It's time to talk about asymptotic methods and special functions. Asymptotic methods. I will look at topics like asymptotic expansions, Laplace method, stationary phase method, saddle point method, steepest descent method, WKB approximation, turning point, and Stokes phenomenon. So, the introduction, uh, in the introduction, we see that asymptotic analysis studies the behavior of functions, integrals, and differential equations in limiting regimes, such as x approaching infinity, epsilon approaching zero, and k approaching infinity. So we study the behavior of functions, integrals, and differential equations in limiting regimes as x is approaching infinity, epsilon approaching zero, or k approaching infinity. Now, these methods are widely used in quantum mechanics, optics, wave propagation, fluid dynamics, statistics, and applied mathematics in general. The key idea is that complicated global behavior is often controlled by local behavior near critical points. I remember as I wrote my final year project as an undergraduate in fluid dynamics, having studied applied mathematics. And I remember I used this asymptotic method a lot. So let's talk about asymptotic expansions. We say f of x is approximately g of x as x approaches a if the limit of f of x over g of x as x approaches a is equal to 1. So the fact that the limit of f of x over g of x is equal to 1 as x approaches a simply means that f of x and g of x are about the same. And that's exactly the kind of situation we have for sine x over x, right? So when we have the limit of sine x all over x as x approaches 0. So that simply, this is 1. So that tells us that as x gets smaller and smaller, as x approaches 0, then it means that sine x is almost like x itself. So that's exactly why sine x over x can be 1 as x is moving towards 0. So this means that g of x approximates f of x in the specified limit, that is x approaching 0. So for example, oh, okay, I think I was ahead of myself with that. Consider sine x, right? As x moves towards 0, so, and what exactly we mean by x moving towards 0 is this. If I go to Desmos, for instance, and if I go to Desmos and I start taking the sine of values, say I start from sine 90 degrees. Sine 90 degrees is 1, right? Let's say I start from sine pi divided by 2. Okay, that's 1, right? And then, so let me just keep making it smaller. Then I have sine, and I also have sine pi divided by 3. So you see it's getting smaller. Then I have sine pi divided by 4, getting smaller. Then I have sine pi divided by 5. It's getting smaller. So let me jump and go to say pi sine pi. Pi divided by 2 is 90 degrees. Pi divided by 4 is 45. Pi divided by 3 is 60. Like that. Um, okay, this should come after this. Okay, so sine pi divided by 6, that's sine 30, that's 0.5. So it's reducing. Then we have the next one, say sine, let me take something very small. 90 degrees is 180 is pi, right? So if we divide pi by, say, pi over 10 would be sine 18 degrees. So let me do sine pi divided by 10. That's 18. So you can see the value keeps reducing. So um let me take sine pi divided by 18. That's 180 over 18. That's sine 10 degrees. So it's that small. So, and it keeps going like that. Let me take sine pi divided by 30. That's sine 6 degrees. And that's 0.10. So if we keep going, let me take sine pi divided by 300. So you see, we have got that's even gone beyond 0. So as this one is approaching 0, right? So sine 0 itself is 0, like that. So let me still try with, say, sine pi divided by, say, 300, 3,000. So we already have zero there. 300, 30, you have 0.1. So, and that's so as x is approaching, is moving towards zero, sine x is moving towards being x itself until we now get to, so sine x is approaching x. So, as a result of that, the limit of sine x by x as x approaches zero is equal to 1. Then we talk about asymptotic series. An asymptotic expansion has the form f of x being approximately theta naught of x plus, this is phi naught of x plus phi 1 of x plus phi 2 of x and so on and so forth. So it means that this expression is approximating f of x, and something close to that would be maybe something like Taylor series. So successive terms satisfy the fact that the phi phi sub n plus 1 of x is of order big small o of phi n of x, like that. So meaning that each term becomes progressively smaller. So imagine this expansion now, expansion of ln 1 plus x. So I think this is Taylor series right here. So the first thing we do is um okay, when x is 0, we have nothing, right? And then, so for small x, if we take very small value of x, we see that ln 1 plus x would be x minus x squared over 2 plus x cubed over 3 minus x raised by 4 over 4, and so on and so forth. Thus, we say that ln 1 plus x is approximately x minus x squared over 2 plus x cubed over 3 as x approaches 0. So we can have a Python visualization of that here. So um, we have this, the exact thing is log 1 plus x, right? Of course, we're taking that from numpy, and the approximation is x minus x squared over 2 plus x cubed over 3. And then we have taken the value of x to be from minus 0.8 to 0.8 in 4 divisions. So we plot x against the exact, we plot x against the approximation, and we see what the connection is like. So you can see the exact thing is the blue one, and the orange one is the approximate one. So you see, as we have more and more terms, the orange line tends to align more with the blue line, like that. Then we have divergent asymptotic series. Many asymptotic series diverge, right? Example, if you have summation from n equals 0 to infinity of n factorial x raised power n, this diverges for every x not equal to 0. So it diverges for every x that is not equal to 0. However, partial sums may still provide excellent approximations. So this is one of the central ideas in asymptotic analysis. So we talk about the idea of divergence here. So as far as x is not 0, we have a divergence. So the values become bigger and bigger. So, and then we go on to talk about the Laplace method. So for the Laplace method, right, we have the Laplace method approximates integrals of the form I of lambda, which is equal to integral from a to b of raised to power lambda multiplied by f of x, then g of x down here, dx, for large lambda. So this dominant contribution, the dominant contribution comes from the maximum value of f of x. So the biggest value of f of x determines what happens to the whole expression. So it dominates the integral. So talking about Laplace approximation, then we have this, that since the dominant contribution comes from the maximum of f of x, so focus a lot on f of x. So here we have that we have the Laplace approximation formula. So suppose f of x has a maximum at x naught. So, and you know how to find maximum based on like calculus, right? You differentiate and equate to 0 and solve for x. So whatever value you get there would most likely will be a turning point, most likely a minimum or maximum point. Then suppose f of x has the maximum at x naught, and the second derivative of x naught is less than 0. This is condition for a point being a maximum, right? If the second derivative, if you evaluate the second derivative at x naught, where f of x is maximum and the value is less than 0, then you can then expand near x naught such that f of x is approximately f of x naught plus half f prime prime of x naught, x minus x naught square. So this is Taylor's expansion for sure, and it is that expansion about the maximum point. Then we can say in that case, if we can get this kind of thing, we can say that the I of lambda is approximately e raised to power lambda f of x naught multiplied by g of x naught down here, then square root of 2 pi all over lambda multiplied by the absolute value of the second derivative evaluated at x naught. So once this condition has been met, then we can have this, we can approximate the integral in this form. So any integral of this form that you have, exponent of lambda f of x multiplied by g of x dx. So you find the maximum point, and once you find the maximum point, then you throw it into this expression, and that will be the approximation for the integral. So we take this example now. So imagine you have to approximate I of lambda, which is equal to integral from 0 to 1 of e raised power minus lambda x squared dx. So in this case, you can identify f of x as you can identify, if you compare term by term, right? F of x, so if you isolate lambda, what will be left here as f of x will be minus x squared. So you can easily forget about the minus, but don't, because lambda is on its own. So you have minus x squared. So for large lambda now, so here f of x is minus x squared, right? Then g of x is 1 because it doesn't even exist. So g of x is 1. So in that case now, for us to find the maximum, right? So you differentiate this. When you differentiate minus x squared, you get minus 2x, right? So minus 2x equals, if you equate minus 2x to 0, that means that x is equal to 0. So that means by the time you differentiate the second time, if you differentiate minus 2x the second time, you get minus 2. So it means at every point, the second derivative is less than 0. So as a result of that, the maximum occurs at x not equals 0, right? So also it means that f prime prime of 0, we also see f prime of 0 is minus 2 because x is even gone. So there's no place to even put that. So the second derivative is automatically minus 2. So that means x of 0 is, by right, the maximum point. And once you get that, all you just need to do is throw that into this expression. So you have e raised power lambda uh, minus x squared. So if you put 0 there, that's e raised power 0 in short, and that will be 1. Then g of x not doesn't is 1. So already gone. So we only have square root of 2 pi over lambda into this left. And the value of f prime prime of x naught is minus 2 that we have here. So you have to now have square root of 2 pi over lambda times absolute value of minus 2. That's 2 pi over 2 lambda, right? And 2 pi 2 pi over lambda into 2. So this is 2, right? This is 2 pi over lambda times 2. Um, so that's 2 over 4 lambda. Normally, right, that should be, we have 2 pi up here, right? Then lambda into 2. So it should actually be lambda over pi if you ask me. I suspect this should actually be lambda over 2 if that answer is anything to go by. So I think this should be lambda over 2 because the 2 cancels out. Yeah. Except there's something I'm not getting right. Yeah. I believe that once this formula is correct, then this is 2 pi up here already, and then we just have lambda times 2. So 2 cancels out. So we just have pi over lambda like that. So if we take lambda from 1 to 50 and we initialize for the exact, and then we have for L in lambda, and we have exponent of minus LXS 0, comma 1, and we append the value into this place and we keep running it like that, and then we have square root of pi over 4 lambda. This would actually be square root of pi over lambda from what I've said, because here now, except what am I not getting right here? Yeah, I think it's fine. This is square root of 2 pi over lambda times 2. So because absolute value of minus 2 is 2, so 2 cancels, so we just have pi over lambda. So I believe this place should be lambda, except there's something I'm missing though. So if you run this now, we get yeah, this is what we get. So you have the exact and the Laplace a bit far away. Okay, let me go back and see what's happening here. So maybe there's something wrong with the formula. So these ones are aligning so well, so well. So should this really be 4 lambda? Let me say again. F prime prime of x naught. That's simply minus 2. And you have 2 pi up there. So I think this needs a lot of reconsideration. So this should not be 4 lambda. But 4 lambda seems closer to the real thing than what we have up there. So let me know what you think about this. You can check what was your observation, or let me check again. Laplace approximation formula. Let me see. Maybe something is wrong. Laplace approximation formula. Approximation formula. Oh, do we have that here though? Laplace approximation formula. Mm, that one involving square roots. Okay, these ones are totally different. Um, Let me go the AI mode. Aha, so this is, yeah, it is 2 pi over m h prime prime of x naught. Yeah, the formula is right. Yeah, the formula is okay. So if that is the case, then this is lambda, lambda. Yeah, so what we have here is correct. So we have to use it exactly what the way we have it. So no worries then. We just have to leave it that way. So here, of course, the gap is a bit wide, but that's what we have in what we have there. Okay, so we go for stationary phase method. So we've looked at expansion formula, asymptotic expansions, right? Then we've looked at asymptotic series, and we've seen an example of an expansion. Then we've looked at divergent asymptotic series. Now we're looking at the Laplace method, and now we've considered Laplace approximation formula. So we go on to the stationary phase method. This method applies to oscillatory integrals like I of k equals integral from a to b g of x raised by I k f of x dx for large k now. So rapid oscillations cancel out except near stationary points where f prime of x naught is equal to 0. That's more like the turning point where you can either get minimum point or maximum point. Then you have the stationary phase approximation, just like we have Laplace approximation the other time, Laplace approximation formula. So for stationary phase approximation, it looks a lot like about the same. So near the stationary point, f of x is approximately f of x naught plus half of f prime prime of x naught into x minus x naught all squared. Then I of k is approximately g of. So once we find this x naught now, the stationary point, so that's approximately g of x naught e raised by ik f of x naught. That's following this integral now. You have g of x naught e raised by ik f of x naught, and you have e raised by I pi over 4 sine, then whatever the sine of f prime prime of x naught, then multiply by square root of 2 pi over k, absolute value of f prime prime of x naught, just like the other time. So we have the Fresnel example, for instance. So you have I of k equals integral from minus infinity to infinity, e raised by ikx squared dx. So the face now is f of x, which is x squared here, because up there, if you remove ik, whatever you have left is f of x. So f of x is x squared. So the stationary point satisfies that f prime of x, which is 2x, is equal to 0. That means that x naught is equal to 0, because if you solve it for x here, that's x naught equals 0. Also, if you do the second derivative, if you differentiate 2x again, you get 2. So whatever happens, okay, here we're not looking for maximum or minimum, we're just looking for extreme point. So with this extreme point now, we say x naught is 0. So x naught is 0. So g of x naught, that is 0. So I mean, but this 0 alone just cancels out every other thing. All right. Okay, this e here is so g of x naught. G of x here, let's see, is 1. So okay, that's just one, so we don't even have it. So for the other one now we have uh of course this will just be 1. Then we just have I pi. Okay, this is e raised by ik f of x naught. F of x is x squared. X naught is 0. So that should go. Then we have e raised by I pi over 4 sine something. So this is e raised by I pi over 4. The sign of f prime prime of x naught is positive. So we just have e raised by I pi over 4 on its own like that. So this one is gone already. So this is 1 multiplied by e raised by 0, which is 1. So 1 times 1 is gone. So we have e raised by I pi over 4. 4 multiplied by the sign that comes from the second derivative. That's positive based on the fact that f prime prime of 0 is positive 2. So we now have ik. I of k is approximately the same thing as e raised by I pi over 4. Square root of pi over K, exactly what the kind of thing I was talking about before. Now this is 2 pi all over K times the absolute value of f prime prime of x, which is 2 again. So 2 cancels out. We just have pi over K here. All right, so that's the approximation there. Then we have the saddle point method. The saddle point method uh, extends Laplace and stationary phase methods into the complex plane. So we have complexity coming into this at this point. So the saddle point method extends Laplace and stationary point method into the complex plane. So if you consider I of gamma, for instance, so we have I of lambda rather, and that is equal to integral along the surface C, then e raised power lambda fz, then multiplied by g of z down there, and d of z like that. So z here is complex. So critical points will satisfy that the first derivative evaluated at the critical point, that's 0. So these are called saddle points in this case for the sake of for the case of complex numbers. So that takes us to the Stirling formula derivation. So if we start with the fact that gamma of n plus 1 is integral from 0 to infinity of e raised power minus x, x raised power n dx, and then we can rewrite this as gamma of n plus 1 equals integral from 0 to infinity. Now, e raised power minus x, x raised power n, so we can tidy up everything together as e raised power n ln x, e raised power n ln x minus this x here. So that's how to tidy this up. So because normally if we break it apart, we have e raised power n ln x minus e raised power e raised power x. And that means that e raised power n ln x is the same thing as e raised power ln x raised power n. So e raised power ln will go. So x raised power n still remains. So this is another way of writing the same thing we have right here. Because x raised power n is the same thing as um e raised power n ln x. Okay, so the saddle point then satisfies that we have d dx of n ln x minus x equals 0. So we differentiate this, right? So we differentiate n ln x, that is n over x, because if you differentiate ln x, you get 1 over x. So you have n over x, differentiate x, you get 1. So that tells us that x is equal to n simply. And if that is the case, then we can say n factorial is approximately 2 square root of 2 pi n into n over e raised power n. So that yields the Stirling's approximation, which you can then check out here, for n in 1, 2, 5, 10, 20, and so on. So the exact factorial we can get, and then the Stirling approximation we can also get from the square root of 2 pi n, which we have down here, multiplied by n over e, that's the value of e, which is 2.718 as usual, all raised to power n now. So if we run this now, we see that for n equals 1, 1 factorial is 1, but the Stirling approximation gives us 0.922, which is which is sort of close. Then for n equals 2, we have 2 factorial, which is 2. That's the exact value is 2. The Stirling is 1.91, which is also close to 2. Then for n equals 5, the exact value is 180, 120. The Stirling approximation gives 118 and all that, which is a bit close. Then for n equals 10, you have 3628800, but Sterling gives us 3598695. Then when you go on to uh, n equals 20, now you have 2432 and so on. Here you have 2422. So as the numbers become bigger and bigger, the Sterling approximation becomes more and more accurate, basically. So that takes us to the method of steepest descent. So, we're talking about asymptotic methods. So the method of steepest descent, that sounds like an optimization thing. It's one of the things I considered under the numerical optimization playlist, which you want to check out if you're interested in that. So method of steepest descent now. This method deforms contours through saddle points along directions where the imaginary value of f of z is constant while the real value of f of z decreases most rapidly. So this transforms oscillatory integrals into exponentially decaying integrals. So that's the method of steepest descent, like that. And then that we move on to the WKB approximation. If you consider that epsilon squared multiplied by y prime prime is equal to q of x y, where epsilon is a very small value. So we can assume a solution of the form y of x equals e raised power s of x all over epsilon, so that we can expand s of x to then be s naught of x plus epsilon s1 of x and so on and so forth. Now we have the leading order WKB. So substituting into the integral equations now, we already have S of x approximated as this. So we can have S naught prime squared to now be Q of x. S naught prime squared is Q of x. Thus, we say that S naught prime is equal to plus or minus square root of Q of x. So integrating that, we then have that S naught of x is equal to plus or minus integral over x square root Q of t dt, like that. So we then have our WKB solution to be as follows. If Q of x is greater than 0, then y of x is approximately c over Q of x raised by 1 over 4 exponent plus or minus 1 over epsilon integral over x of square root of Q of t dt. Then if Q of x is less than 0, so we have the same expression, except that now we have instead of just Q of t, we have absolute value of Q of t. So in case because here Q of x is negative, so we guarantee that it's not negative here by applying the absolute value. So now we go ahead to talk about turning points. Turning points occur where Q of x is equal to 0. So at this point, the WKB approximation breaks down because the factor Q of x raised by minus 1 over 4 becomes singular, right? Because we see that Q of x there is equal to 0. So example of that is when when we consider epsilon squared y prime prime equals 1 minus x squared of y. So, this is like our Q now. If you follow the original template, so the original thing is epsilon squared y prime prime equals Q of xy. So it means that our Q of x here is 1 minus x squared. So turning point occurs where we have 1 minus x squared equals 0. Thus, we say that x is equal to plus or minus 1. So for the absolute value of x less than 1, we have oscillatory solutions. When the absolute value of x is greater than 1, we have exponential solutions in that regard. So, and then we can have that plotted here. So looking at the code, we take it over x from minus 2 to 2, and q is 1 minus x squared. Then we plot x against q, and we have this plot right here. Of course, 1 minus x squared tells us that we have solutions at minus 1 and plus 1, just like we saw before. So we have the turning point there. So then that takes us to Airy equation near turning point. Interestingly, the next video is going to be focused totally on Airy equation near turning points. So near a turning point, equations reduce to the Airy equation where we have y prime prime minus xy equals 0. And the solutions are ai of x, bi of x. So this connects oscillatory and exponential regions smoothly. Okay. So, and then we have the Stokes phenomenon. Different asymptotic terms may switch on or off across certain curves into the complex plane. So these curves are called Stokes lines or anti-Stokes lines. This phenomenon explains sudden changes in asymptotic behavior. And we have an example in the Airy function where we say for a large positive value of z, I of z is approximately e raised by minus 2 over 3, z raised by 3 over 2, all over 2 root pi, then z raised by 1 over 4. So across Stokes lines, we have additional exponential terms appearing. Then in summary, we have that we have the following, we have the methods and the main idea. For asymptotic expansions, we have approximate functions in limiting regimes. Laplace method, we have dominant contribution from maxima. We talk a lot about the fact that the maximum of x dictates what happens. Then we have stationary phase, oscillatory integrals dominated by stationary points, then saddle points, complex plane, critical points. Then we have steepest descent, that's contour deformation along rapid decay. Then for WKB, we have exponential approximation of ODEs. For turning points, we have breakdown of WKB, and Stokes phenomenon talks about switching of asymptotic terms. So final remarks. Asymptotic analysis is one of the most powerful tools in applied mathematics. The essential philosophy is identify dominant contributions, 1, 2, approximate locally near critical points, 3, extract global behavior from local structure. That is that is the essence of asymptotic analysis. So these methods form the foundation of semi-classical quantum mechanics, wave propagation, optics, perturbation theory, special function theory, and statistical mechanics. So we have practice problems as usual, of which I'm going to solve four. I'm going to solve two rather. So I'm solving problems 4 and 13 here. Problems 4 and 13. So show that the square root of x squared plus 1 is approximately x plus 1 over 2x minus 1 over x cubed. Now we can use the Taylor's expansion for this as x approaches infinity. Then obtain the first four terms of this I mean, this is just the same thing as 1 plus x raised to power minus 1. So you just keep expanding. Then 3, uh, find the asymptotic expansion of arctan x. That's arctan x, right? As x approaches infinity. We can do that too using Taylor's expansion. Then you have using Laplace method, approximate this, you know. So here we just identify f of x. Oh, this is what we're going to solve, by the way. So you just identify your f of x as minus x squared plus 2x, then differentiate, equate to 0, solve for x, and then throw it in, do the second derivative to establish whether the turning, you have one of the turning points as maximum. If you have more than one turning point, I think you're going to have just one turning point, by the way. So I can check if it is a maximum point and then use the approximation for that. So you're going to do that. Then use Laplace method to estimate this for large n. Then 6, approximate this also. So it looks like what we have up there. Then we have 7, 8, problem 7, 8, and 9. Yeah, we can have up to 9. Then problem 7, 8, 9. Then we have 10, 10, 11, 12, 10, 11, 12, and 13 here. 10, 11, 12, 13, like that. Then 14 to 18. Okay, let me just say 14 to 17. 14 to 17. Then we can see the rest. We can see the rest. So explain why the YKB approximation fails near turning point. So let's solve the two problems we have to give as example. So, okay, problem 14 is the next one we're solving, right? It says apply the WKB approximation to epsilon squared y prime prime plus x squared y equals 0 and determine the oscillatory behavior. So we're going to do 4 and 4, 4 and 13, yeah? Is that 13? 13. No, 13 is different. So use WKB to obtain an approximate solution of epsilon squared y prime prime equals x plus 1y for small epsilon, like that. So here now we then have this. Yeah, problem. So we start with problem 3, problem 4. Problem 4, which says using Laplace's method, approximate I of lambda, which is integral from 0 to infinity of e raised to power minus lambda into x squared plus 2x dx. Okay, for large lambda, So we go for that and have the solution. The first thing, you identify the phase function. So first step is to identify the phase function. So to do that, we write the integral, in the standard Laplace form, in the standard Laplace form, which is just this. That is I of lambda equals integral from 0 to infinity, e raised to power minus lambda f of x. No, e raised to power lambda f of x dx. This is the standard form. So we are comparing this with what we have now. I of lambda equals integral from 0 to infinity e raised to power minus lambda x squared plus 2x dx. So that simply tells us that, if you isolate the lambda, whatever we have left is f of x. So this is f of x. So minus here together with this will be our f of x now. So in that case, uh, so we have that f of x is equal to minus x squared plus 2x. So because we know f of x, the maximum value of f of x determines what happens with the rest. So the next thing we are going to do is to find the maximum point. So to find the maximum point, we have f prime of x. You differentiate the function and equate to 0. You have f prime of x. So when you differentiate this, you get minus 2x plus 2, right? When you differentiate this expression, you get minus 2x plus 2. So and then you equate to 0. So f prime of x equals 0 simply means that we have minus 2x plus 2 equals 0. So in that case, we have minus 2x minus 2 equals 0. That means minus 2x is equal to 2, and that means that x is equal to 2 over minus 2. So x is equal to minus 1. So that is uh that is a turning point. Okay, but we are not sure. We have to confirm further that it is maximum point. What do we do? So we do to confirm nature, to confirm. So for now, it's a turning point. To confirm the nature, because if you have more than 1 point, you have to identify just the maximum point. To confirm the nature of the turning point, of the turning point, what do? We need to find f prime. We already know f prime of x is equal to minus 2 is equal to minus 2x plus 2. So second derivative now, f prime prime of x, that is minus 2 easily. So whatever happens, whatever we got there is actually maximum point. Therefore, x naught is equal to minus 1 is the maximum point. It's the maximum point. So with that out of the way, then we can move on to say that okay, I mean, you see x naught is minus 1, but the integration we have is over from 0 to infinity. Okay, so since the integration, the integration interval is 0 less than or equal to x less than infinity, what that tells us is that the critical point, the critical point lies lies outside the interval. It lies outside the interval. So what does that mean? We say, thus, the dominant contribution, thus contribution, the dominant contribution comes from the endpoint. It comes from the endpoint. Endpoint x equals 0. Okay, x equals 0. Now, because the maximum value, the maximum point we got is minus 1, and that is outside the range. So the closest endpoint to it is 0. So it means that the dominant contribution comes from the endpoint x equals 0. So if that is the case, then we can expand near the endpoint. So expanding, expanding near x equals 0, which is the endpoint, near x equals 0, we have f of x equals minus x squared plus 2x. So for small x, right? For small x, f of x will be approximately minus 2x. Okay. Since the linear term dominates, for a very small value of x, right? Um, x squared will be small, very small compared to 2x for very small values of x. So since the linear term dominates, thus we say that I of lambda is approximately integral from 0 to infinity e raised to minus 2 lambda x dx. So with this now, we can then evaluate the approximate integral. So evaluating the approximate integral, evaluating the approximate integral, we have integral from 0 to infinity e raised to minus 2x dx. That is equal to 1 over 2 lambda. Okay. Therefore, 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 I of lambda is approximately 1 over 2 lambda as lambda approaches infinity. As lambda approaches infinity. So that's how that goes. Then we come for problem 13. So for problem 13 now, problem 13. So want to identify, you want to use use WKB, use WKB to obtain an approximate solution, an approximate solution of epsilon squared y prime prime equals x plus 1 y for small epsilon. For small epsilon. So the first thing we want to do is to identify the WK form. So the equation, the solution now, the equation for the WKB form rather, or the WKB form is epsilon squared y prime prime equals q of x y with, so in this case now it means that if you compare this with this, every other thing is intact except for q of x. So it means q of x will be equal to x plus 1. So we say with q of x equals x plus 1. Okay, so then we need to now assume. So assume that y of x now is equal to e raised by s of x all over epsilon there. So we substitute into the equation. Substitute into the equation. And if we do that, we see that the leading order WKB equation becomes S naught prime squared equals Q of X. So S naught, because this SX can be expanded, like that. So the leading term is now that the leading order YKB equation becomes S naught prime squared, which is equal to Q of X. Thus, we have S naught prime squared to be equal to X plus 1. So that means that we have, if you take square roots, that means we have S naught prime to be square root of X plus 1. To remove this root now. So that's X naught prime equals square root of X plus 1. Of course, that's plus or minus square root of X plus 1. So the next thing we have to do is to integrate. Integrating, we have S naught of X. If you integrate S naught prime or X naught prime, you get S naught, right? So S naught of X is now plus or minus integral of square root of X plus 1 dx. Okay, so here we can use substitution method. So we can say, let u be equal to X plus 1. So if u is equal to X plus 1, that means we can also get du. So that means du dx is equal to 1, which implies that du is simply dx. So we can then go back into the expression and we then have that S naught of X is equal to integral, integral square root of u du, right? Yes, square root of u du. That's what we can have for that. And that means we have integral u raised by half du, which is equal to, if you integrate u raised by half, you have u raised by half plus 1 all over half plus 1 plus some arbitrary constant, right? And that will be u raised by 3 over 2 all over 3 over 2. So if you tidy that up, that means we have, okay, let's not forget the plus or minus that we're coming with. Okay, so that means that we have, okay, in this realm, right? Let's leave it the way it is, first of all. Then when we come back to X, bring it back. So this is now 2 over 3, u raised power 3 over 2, u raised power 3 over 2. But you won't forget, this is now this is S naught of u, not X anymore, because we've changed dimensions. S naught of u. So that means S naught of u is this. Uh so we then remind ourselves where we are coming from. Therefore, S naught of x is equal to 2 over 3. Don't forget your u. The u we started with was x plus 1, right? Raised power 3 over 2. Now we have plus or minus. So S naught of x is equal to plus or minus 2 over 3 into x plus 1 raised power 3 over 2. So of course you can rewrite that in some other ways. So you have plus or minus 2 over 3. Square root of x plus 1, of course, is this, x plus 1. And then you have that power. So you can write it like this if you like. So, what we need to do, what's the question again? We have this to, we have to use WKB to obtain an approximate solution for this, for small epsilon, right? So what we have got so far is just S naught of x. We still have some movement to do. So the next thing is to construct the WKB solution. So we know that the standard WKB solution is y of x, which is approximately c over q of x raised by 1 over 4, then exponent into plus or minus 1 over epsilon integral over x q of t, square root of q of t dt, like that. So substituting q of x equals x plus 1 now. So we have okay, that gives y of x approximately c over x plus 1. Y of x is approximately c over x plus 1 raised by 1 over 4, then exponent plus or minus 2 over 3 epsilon x plus 1 raised by 3 over 2, like that. Yeah, all that is already integrated. So we have this. So we can expand that, right? We can expand that because this is plus or minus here. So we can have it as a sum of the two terms, like that. So we have y of x is approximately c1 all over x plus 1 raised by 1 over 4 exponent 2 over 3 epsilon, then x plus 1 raised by 3 over 2 plus c2 all over x plus 1 raised by 1 over 4, then exponent minus 2 over 3 epsilon x plus 1 raised by 3 over 2. And that is the final result in that regard. So with that, we come to the end of asymptotic methods. So I'll flash the practice problems once again for you to see, and then it will be done. Okay, so you have problems 1 to 3 here. Then, okay, again, problems 1 to 3. Then to 4 to 6. 4 to 6. Then we have 7 to 9. 7 to 9. 10 to 13. 10 to 13. Then 14 to 17. Then 18 to 20. Okay, so with this, we come to the end of this interesting video talking about asymptotic methods as far as special functions are concerned, right? So asymptotic methods help us to get solutions, but to difficult integral, difficult differential equations, and difficult expressions by, understanding what happens at turning points, right? So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges you find when you click on join. Ultimately, don't forget to comment, like, share so that other people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.